Welcome to this presentation of our project. My name is Rodrigo Moreno. I will present our project that is called Characterization of the Mechanical Tissue Properties of the Brain in the Developing Brain with Magnetic Resonance Elastography. And this is a collaboration between me and Armite Goldkar from the Psychology Department at Stockholm University. Yes, so we are interested in the developing brain and anxiety disorders. It has been shown that especially a time that comes from the childhood and adolescence represent the peak age for the onset of the anxiety disorders. And we know that in adolescence, the brain has a dramatic neurodevelopment. Something that has not been tested so far is the mechanical properties of the brain, and we would like to know if changes in these properties has something to do with the anxiety disorders. So this is the main point of the project. So is to answer this question. Are these changes related to the risk of developing anxiety disorders or not? So our approach to answer this question is to compare two groups of children. So one is between 9 and 11 years old, so before the onset, and then 13 and 15 years old, where it's supposed that they are already like passing this onset age. And we are going to use MRI, especially two techniques that are new. One is called MR elastography. I will talk more about that here, and also brain connectivity. And then the idea is to see if we can use this imaging data to distinguish these two groups between children and adolescents. And then we are going to run a battery of tests to assess predictors of anxiety in these two groups. And then the idea is to correlate these factors, risk factors given by the questionnaires, with the findings from the imaging. Yes, so then the main instrument that we are going to use here is magnetic resonance elastography. It's a novel technique that uses MRI to measure the mechanical properties of the brain. And this is how it works. So we have the MR scanner that we have at KTH, and then we have a pneumatic driver that is pumping air to a pillow that is situated behind the head of the subject. And then we acquire images. And then once we have these images, we have to do some post-processing to get the actual maps of the properties of the brain. And we are proud that KTH is the only site in Sweden with this technology. So yeah. MRE, so then we can see the different ingredients you need to have for doing these studies. First, you have to have, of course, the scanner and the pump that I just mentioned, and the pillow that is here. This is the actual pillow that we are using. And then, as I said, there is like a small movement of about 5 to 10 micrometers with high frequency in the brain. So the feeling is that it's like these electrical toothbrushes. So it's very mild. And then we have to program the MR scanner to get these images of these waves that are inserted into the tissue. So this is done with this motion encoding gradients that are synchronized with this external motion source that I was mentioning. And then this should be done in XYZ and different phases. And then once we have this, we have something like this, that is like the waves propagating in the brain. And then after this inversion, then we get the maps of different properties of the brain. And this is how it looks, MRI in our scanner. So as you can see, these are the waves that are propagating in the X, Y, and Z direction. And then these three maps that are like, as you can see, waves is called wave maps. You can use all this information to get this elastogram that tells you how stiff or how soft the tissue is in the brain. And you can compare it with the anatomical images here. In this project, we are developing new techniques for doing this inversion. It's challenging because you need to have very advanced techniques for doing this. Usually, the techniques that you are using are based on finite element model, so then it takes hours to reconstruct one image. So we are going to use artificial intelligence to speed up this process. So there are methods for doing that, but so far they are very restrictive. So we are going to extend this previous work with real data that we are acquiring in our scanner. And then we are going to use something, a new technique that is called physics-informed neural networks. So far, we have been also working in an MRI simulator because then, since we are interested in using artificial intelligence, these methods require a lot of data. And then in the world, there are like very few data sets that are publicly available, basically because MRI is a new technique. So people are still in the process of getting the techniques to work and start sharing data. So since we want to use artificial intelligence, we need a lot of data, which we can create with simulating data. So here we implemented a paper that where you could introduce the model of the brain. That this model was developed by KTH, our colleagues from the neuronics engineering, and this is an FEM model. So then we applied the input also like the external actuator to simulate this movement of the tissues behind the head. And after simulations, we get the waves images that look like this. So with this, we can have everything, because then we have the properties of the brain that we can put in our model here. And with those, we can simulate them to get the wave images. And then we can have everything we need for training our model. So then is the, let's say, ground truth that we are putting here in this model, and the waves that are generated with this MRI simulator. So the goal here is to have a lot of images generated with this simulator, and in a second step, then we will fine-tune the neural network to take care of the particularities of the imaging acquisition that we are getting from our KTH scanner. This is basically it for now. So we expect that next time we will have much more results. We are getting closer, and we are starting a lot of acquisitions with the children. We are contacting already schools in Stockholm to get children from these ages that I mentioned, and then soon we'll have some more these results to show. And we hired a postdoc for this project, and then this is also a collaboration with Joe that is working with the simulations. And this is in collaboration also with Mayo Clinic, that has provided us with sequences for MRI for the brain, and the people from Philips that have been very, very helpful for this project. Thank you.